Hi, I'm Lewis Carroll Epstein. I'm going to give a few talks and tell a few things that I know about physics. I want to give you a little taste of physics itself and work out a little physics questionnaire. And I'm going to start at perhaps one of the oldest problems. Way back before Newton, there was a physicist called Archimedes. And he thought about the rules for why things floated and how they floated. And that's what I'm going to talk about. Can a battleship float in a bathtub? Let me draw a picture of the situation. Here we're going to have an old clawfoot bathtub. And in this bathtub, we're going to put a battleship. Imagine either that you have a very big bathtub or else a small battleship. It's there, it's hanging there. It's not touching the tub. All around the battleship, underneath the battleship, in the front of the battleship, in the back of the battleship, all around it there's a tiny little space. It's just enough space to slip a dime, so you can just slip a dime under it. But it's not touching. Something is holding it up. And now we're going to do something. We're going to add some water. We're going to pour water into this thing. And how much water are we going to pour into it? Well, there is marked on the side of the ship a red line across the ship. And of course, ships are supposed to sink down to this red line in the water. And so we're going to pour water in, and we're just going to pour enough water in to fill up the ship like this. It's all around on the side of the ship. And the question that I ask is, what's going to happen to the ship? Is it going to float or is it going to sink? Some people will recite a rule from deep in their memory that a ship must displace its own weight in water. Okay, well, you say, what does a ship weigh? Well, I don't know what the ship weighs, but it probably weighs hundreds of thousands of tons. How much water is in here? It doesn't have to be very much water. It could be a very, very thin layer of water. Well, one thing might happen. Maybe the ship will float just the way it is. Maybe nothing will happen. The thing will just stay there. On the other hand, another possibility is that the ship will crash down to the bottom of the tub and a great big old jet of water will squirt out here and another big old jet of water will squirt out here and the water will go flying out and crunch. The boat will fall down to the bottom of the tub. Heavy boat will just push the water right out of there. Of course, I suppose there's a third possibility. Maybe that's that the water will go down and it'll push the boat out, but I don't think anybody takes that very seriously. How are we to think about this? How are we to reason out what the answer is? What I'm really interested in is the story that leads up to the answer. Floating is a complicated thing. If a thing floats, if it doesn't float, how high it floats. Floating is complicated. A big rock, a big heavy rock, that surely won't float. Does water have any effect on a big heavy rock? Years ago, I was up high playing in a small river. And down at the bottom of this river, there was a great white quartz boulder. And I went over and I began looking at it, playing with it. I was up to my waist in water. Pretty soon I picked it up. I bent over and I picked up that rock. And I was astonished that I could pick up that big boulder. After I picked up that boulder, I tried to pick up some other boulders. I found I was literally Superman. I could pick up these enormous boulders underwater. So I picked one up and I began walking towards the edge of the river. There's a little beach there. And I began to walk up on the beach. And as I walked up on the beach, remember this rock I was picking up was always under the water. And finally, as I began to walk up on the beach, this rock began to come out of the water. And as it became out of the water, I found out I wasn't Superman after all. The rock got really heavy and I had to let it go. But as long as that rock was under the water, it was easy for me to pick up. So it's a fact that things underneath the water, even rocks, though there's no chance that the rock is ever going to float, nonetheless, the rock is a lot lighter underneath the water. What makes the rock lighter underneath the water? You might guess that the water insulates the rock from gravity, and the water prevents the Earth's gravity from getting to the rock. The water insulates the rock from gravity. The experience, if that was so, then people in submarines, when they weigh themselves, if a 200-pound man gets into a submarine and he weighs himself, he should weigh less than 200 pounds. But of course, the person in the submarine will still weigh 200 pounds. So what effect does the water have? It has something to do with the water's pressure. That's what makes the rock underneath the water weigh less than when the rock is above the water. Okay, but which way? Which way does water pressure push on things? Here's a tall can of water. Put some water inside. Does that water pressure push down on the bottom? Sure, it pushes down on the bottom. You know it pushes down on the bottom because if you put it on a scale and the scale weighed it, the scale, of course, it would be the water pressure pushing down. But there's another way you can tell, too, that the water is pushing down. Simpler than that, you simply punch a hole in the bottom of the can and the water squirts out the bottom. That shows that there's pressure on it. If it wasn't pressure, it wouldn't squirt out the bottom. Does water pressure push up? Yes, I can show that. Suppose I make a little side pipe coming off like this, and I cap it off. And then I puncture a little hole in the cap. What's the water going to do? It's going to squirt out of here too. The water pressure pushes up. Does the water pressure push to the side? Well, of course, you know it pushes to the side too, because if I punch a hole in the side, water will squirt out of the side. So the water pressure, it turns out, pushes in all directions. It pushes down, it pushes up, it pushes to the right, and it pushes to the left. Which way does the water push harder? Does it push harder down or does it push harder up? After all, you might think it wants to go down, so you might think, well, it pushes up, but it really pushes harder down. It pushes up a little bit, but it pushes down a lot. Is that true? We'll imagine that we color different layers of the water with different colors. But we'll say the top layer of water is colored red. And then we'll have a very thin layer of water that's colored white, and under it, the rest of the water will be colored blue. Question: does the red water push down on the white water? Well, it must. Water pushes down. Well, look then, if the red water pushes on the white water, why doesn't the white water go down? The only reason it doesn't go down is because the blue water underneath must be pushing back up on it. How hard must the blue water be pushing up on the white water? The blue water has to be pushing up on the white water just as hard as the red water is pushing down, because if that wasn't so, the white water would take off. So you can see that however hard this is pushing down, this must be pushing up. So the down push pressure in water is equal to the up push. Now what about the right and left push? The funny thing, it doesn't take much proof, but you just have a feeling. You just have a feeling that the push, however hard this water is pushing to the right, or pushing to the left, it's pushing to the right just as hard. The push to the right and the left. It's funny. People have that feeling for right-left symmetry. That idea comes back over and over and over again in physics, that if a thing looks the same on the right and the left, it works the same on the right and the left. In fact, you get a feeling that space itself cannot tell the difference between right and left. Physicists thought that for hundreds of years, and finally it turned out that in some things in modern physics don't work that way. The right and the left are not exactly the same. But for most of physics, you can be sure that right and left follows your intuition. It's the same to the right and it's the same to the left. Well, now what have we established so far? We've established that however hard the water pushes down with pressure, the water under that pushes up just as hard. We've also established that however much the water pushes to the right on one side, it pushes to the left on the other side. I'll show you another way to see that it pushes to the right and the left just as hard, aside from puncturing holes in it. Let's assume that it pushed harder to the left and didn't push as hard to the right. Pushed hard this way. And you could take this whole shebang and put it on wheels. And what would it do? Take off by itself, isn't that right? If it pushed harder to the left than the right, you'd have a motor that wouldn't just begin going off by itself. So it won't do that. So there, you know, it pushes to the left as hard as to the right. Well, now I want to ask another question. This push balances that push. This push balances that push. Does it push up and down harder, or does it push right and left harder? Which way is it pushing harder? Up and down harder, or right and left harder? Stack of bricks like this. And there is an enormous push down on these bricks due to all the weight here. There's a great push down. But is there very much push sideways on these bricks? It doesn't, there's not much push this way. There's a great push down. So you can't always be sure that the down push is equal to the sideways push. In this case, it certainly isn't. But of course, this isn't what we're talking about. We're not talking about bricks. We're talking about water. Is the downward push in water equal to the sideways push in water? You can answer that question by thinking about little bubbles in water. Suppose we have a glass of water here, and we go in the water, and we see not a big bubble, but we see a little tiny bubble. What shape are little bubbles? Little bubbles are round. That tells us something about what's happening inside the water. Let's pretend for a minute that in water, there was a big downward pressure and a big upward pressure to balance it, but there wasn't much sideways pressure. And what would happen to a little bubble if that were the case? There'd be a big pressure pushing it down from the top, isn't that right? But not much pressure around the side. And you would squeeze the little bubble like this, and the little bubble would come out to the side. It would shape itself not like a sphere. The little bubble would shape itself like a hamburger, squashed like that. That's how the little bubble would shape itself. On the other hand, let's look at the other way. Let's pretend, just for the heck of it, that there was a whole lot of pressure coming in from the side on the little bubble. That we lived in a place where the water exerted a lot of sideways pressure, but there wasn't very much up and down pressure. Then what would the little bubble look like? Well, if you have something that you squeeze in from the side, and the little bubbles would be shaped like this. It'd be long and thin. I ask you a little question. How are little bubbles shaped? We already agreed. Little tiny bubbles are round. You push in to make a meatball, you push in equally hard in all directions. And that is why little bubbles are round, because the pressure in the fluid is the same in all directions. However hard it pushes down, there's a pressure pushing up just as hard. However hard it pushes down, it pushes to the sideways just as hard, pushes both in all directions just as hard. Inside of water, which way it pushes in all directions. There's no preferred direction. Now something happens, and this happens over and over again in physics. When you begin to try to understand physics, the physics of anything, the first thing that happens is that you find that you're getting dumber, not smarter. Let me show you. Why were we interested in pressure? Because I wanted to explain to you why it was that when you put a rock, there's the creek, and here's the rock. I wanted to explain why it was that that rock seemed to lose weight, why it was that the rock weighed less underneath water. Obviously, if it's easier to pick it up, the water has to be doing something that makes it easier to pick it up. The water has to be giving a helping hand. In other words, the water has to be pushing up on it from the bottom. That would help lift it. That would make it weigh less. And we could say, well, that's the water pressure. You see, that's the pressure in the water that's making the rock weigh less. But after thinking about this a little bit, we find out that the water just doesn't push up from the bottom. The water pushes from the side and from the top. And it pushes in all directions just as hard. So if you think about this, all this water pressure pushing on the little rock, this effect is going to cancel this effect is going to cancel this, and so all the pressures are going to cancel out, and the rock's going to have its weight, all the weight that it had to begin with. You're not going to get anything that's going to help you lift the rock. But of course, something has to be wrong someplace here. We must have made a mistake, or I must have made a mistake someplace, because the rock really does lose weight underneath the water. Everything I've said is true. There's only one thing that I forgot. The pressure at any place in the liquid, if we go down into a liquid, have a lot of water to work with, so we'll move the water level up to the top of the blackboard. It's true that if we go to any little place inside the liquid, the water pressure that's pushing this way on this place is equal to the pressure that way, and the water pressure this way is equal to the pressure that way at that place. But what about at some other place, up here? Is the water pressure up there the same? And of course, you know the answer is it's less up there. And if we go down here, what about the water pressure? Down here, the water pressure is greater. We have to remember that water pressure increases as you go down into the water. How do you know that? Well, you know it by common sense. If you've ever gone into a pool, you can feel it in your ears. But it's nice to see why it has to be that way. The reason that the water pressure has to increase as you go down is because what's the cause of the pressure down here? Here's a tall glass of water. This water up here has weight, and this weight is pushing down. And so the water under it has to push back up. Now, suppose we have more water on top, then we have more weight. In fact, if we go through twice as much water, we have twice as much weight, 3 times as much water, 3 times as much weight. So it's the weight of the water, and the further you go down into the water, the more weight of water you have over your head, and that's why the pressure increases continuously as you go down. Back to the problem, why does the rock weigh less? Here's the water. Here's the rock under the water. Sure, the water presses down from the top. Sure, it presses up from the bottom, and it presses from the right, and it presses from the left. But is the pressure the same in all directions? No, it's not the same, because the bottom of the rock is deeper down. It's further down in the water, so the pressure down here has to be bigger. You have more pressure on the bottom than you have on the top. And so there's more force. See, now this force does a little harm, but this is more than enough to overwhelm it, and that's why you get a net lifting force on the rock, because the water down below. Also, I pulled a little trick on you. When I talked about bubbles in water, I was very careful not to talk about big bubbles. Big bubbles have weird shapes, but I talked about little bubbles. That was so I could stay in one place where there would not be much difference. There, the bubble would all be down pretty much at one level. And that's the reason. Now we're beginning to understand. This principle doesn't just work for rocks underwater. It works for other things too. Oh, things like the Goodyear blimp. Thing's pretty heavy. Stays up in the air though. What makes it stay up? I'll tell you what makes it stay up. There's weight in this thing. I mean, after all, there's airplane motors here with propellers making the thing go. So it's a heavy thing. The air is pressing down on it with atmospheric pressure on the top. And of course, there's pressure on the front, and there's pressure pushing on the back. And there's pressure pushing underneath, the atmospheric pressure pushing on the thing. But is the pressure under the blimp the same as the pressure on top? No. The pressure on the bottom has to be a bit more because it's deeper in the atmosphere. Just like the fish live under a sea of water, we live under a sea of air, and as you come down to the surface of the earth, the pressure gets greater. The bottom of the blimp is closer to the surface of the earth than the top, and the air pressure on the bottom is greater than on the top. Just enough greater to make the thing float. That's what makes the thing float by itself. We'll come back to that and talk a little bit about that again, but I wanted to put another question to you. What things affect the pressure of a liquid? I'm going to talk about it in a more practical way. We go up again, back up into the Sierras, and they have these dams up there. And here I'm going to draw 2 dams. There. Okay. There's a dam, and behind the dam we have the thing filled up with water. This dam has to be strong because if the dam broke, out would spill all this water and it'd go down this canyon and drown a whole bunch of people. Now, here's another dam. This is a tiny dam. There's just a little lake behind it. Here, see, this is the lake behind this dam. Not much water. This dam has all this water behind it. This dam just has a little bit of water behind it. Of course, these dams have one thing that's the same, the height of the water, this distance. From the top of the water down to the bottom of the lake, that's the same. But obviously this dam is much bigger, a lot bigger, a lot more water behind it. Which dam has to be built stronger? Well, say the dam that has to be built stronger is the dam that has the most pressure against it. Well, probably right. Which dam has the most pressure against it? Maybe this one has the most pressure against it because it's got the biggest lake, so it has to be built big and strong. This one can kind of make that one cheap. Hasn't got much water, hasn't got much pressure. On the other hand, you could say, well, look, this one, I don't know, that water is squeezed into a very tiny volume, and since the water is so squeezed down here, maybe it has the most pressure against it. And this dam has to be built big and strong. This one can be weak. So how do you know which one has to be strongest? Well, in your imagination, you can do something that will answer the question. What you do is you take this dam down here, carry it over here, and that's what we're going to do. We're going to take this dam, and we're going to carry it over here and put it over here. And then we carry the water across. The water's just as deep as it was before, and there is the water. See, little tiny bit of water in there behind this dam, just a tiny bit of water. This one's got a whole huge lake. There's just a little sliver of water, but there's one thing that's the same. The depth here. See, the depth of this water here is the same as the depth of the water here. Notice how many feet you'd have to dive down to get to the bottom of this lake is the same as this lake. Now, which dam has the most pressure on it? Well, let's think. Way to tell is to make a hole any place you want, but let's say down at the bottom. Make a hole through there, and we'll run a pipe. A pipe goes through this dam, across the intervening space, in through this dam and into this lake, through the pipe. So now water can go back and forth through here if it wants. Now let's pretend there's more pressure over here in the big lake. If there's more pressure here and less pressure over here, then the water is going to go into the pipe, be forced in here and come out here. But if it comes out here, it has to go into that lake. So what's it going to do to that lake? It's going to make this lake go up, and it's going to make this lake go down. Isn't that right? So the water level won't be the same. The water level started out being the same, but it won't be the same. Could that be? There's two things. We know from experience that if you have two bodies of water connected by a pipe, the water level is going to be the same on both sides. It doesn't get high on one side and low on the other. Water seeks its own level, and no water would not go from here over to here, and water would not go from here over to here. In fact, no matter where we make this pipe, we can cut another pipe in up here, cross like that. Would any water go through this pipe? The answer is no. It would fill with water, but after it filled, there would be no water, which means that the pressure at this end has to be the same as the pressure at this end. So no matter where in these two dams you made pipes, you'd find the pressure was the same, which means that the pressure in these two lakes is the same. The pressure doesn't depend upon how much water is back here in the lake. It doesn't give a darn about that. It's just how deep the water is that makes the pressure against the dam. It's the water right up against it that makes the pressure against it, and that pressure depends upon how deep it is. And this little bit of water right here, it's enough to make the same pressure that all this water back here makes. The pressure on this dam is the same as the pressure on this dam. The pressure only depends upon how deep the water is. So now we've learned a few things about the rules of pressure. We've learned that the pressure pushes equally in all directions. We've learned that the pressure increases with depth, and it only depends upon depth. It doesn't depend upon how fat the glass is. The pressure at the bottom of a skinny glass is the same as the pressure at the bottom of a fat glass, just provided the two glasses are equally deep. That's the only thing the pressure has to do with. Let's go back to the battleship. We know that you have to get a certain pressure underneath the water in the ship. We have to get a certain pressure down here underneath the ship in order to keep it up, a pressure in the water. And we know that the ship is filled up with the right depth of water because we agreed that we would fill it up to the red line being painted on the side of the ship. But we just have a tiny little sliver of water that's coming down there. Can this little bit of water give the pressure? But we already established that a very narrow, doesn't care how wide the water is, just as long as it has the right depth. When you get down at the bottom, it will have the right pressure. But when it gets down here, you say it's pushing down. It has to push sideways. Yes, the pressure, if it has the pressure down here, that pressure pushes sideways too. And then the pressure it pushes sideways has to push up. But we know that if there's a certain sideways pressure, the up pressure has to be the same. And so we can put all the lessons together that we learned, that the pressure depends only on the depth, not on the width of the water, that it pushes in all directions, it can push around corners, we can combine all those things and see that the pressure gets communicated around to there. We could do it in another way. We can take the ship out and put it in the ocean. Here's the ship floating in the ocean. Will it float in the ocean? Well, sure, it'll float in the ocean. And now we can imagine that the ocean freezes, that the ship went too close to the South Pole, or maybe it's a terrible winter. This part of the ocean freezes and turns to ice. And then we'll imagine that this part of the ocean freezes and turns to ice. But this ocean gets so cold that the bottom freezes too, and the bottom freezes. And there's ice on the bottom, and then it freezes more. The ship itself just stays warm next to the ship. See, this freezes, and then this freezes, and then this freezes. And finally, we can get to a situation where it freezes, except what? There's just a bathtub left. And you can see that it has to float. Incidentally, this argument about letting the ocean freeze gradually around the ship, it's a cute argument, but it's more than cute. It actually uses an important principle of physics. There's something in physics called the correspondence principle, and it's used a lot in modern atomic physics. And the correspondence principle works this way. You start with a situation that you're familiar with and that you understand. And then you gradually let that situation change little by little by little by little until you get into the weird situation that you don't understand. But as you let it change, you carry along what you know, and you try to work by your imagination from the situation that you know to the situation that you don't know. In this case, we used the correspondence principle by starting with an ocean, which we understood that the ship should float in it, and gradually we let the ocean freeze and turn to something that was not water, to ice, and we saw that we could get into this situation and it would still be okay. So we went from one situation to the other. The correspondence principle is used a lot in atomic physics and quantum physics. And in that case, you start with things that you understand, like pendulums and planets. And then they got smaller and smaller and smaller and smaller. And from that, you work to the situations that must hold for atomic physics. On the other hand, you can also work backwards. Supposing you get some result in atomic physics that seems weird and it just seems it's hard to believe. Well, then you can use the correspondence principle to check if it's right, because if it's right, then you imagine the atom should get bigger and heavier and bigger and heavier. And finally, if you use the rules right, when the atom gets bigger and heavier, you have to come back to the same rules that hold for planets and pendulums. So using a correspondence argument, you use that all over physics. We can see that the battleship will, if it will float in the ocean, then it will float in the bathtub. That's what we know. So what determines if a thing will float or not? I want to talk a little bit about that. Let's go back to our lake again. And I want to take a plastic baggie. And this little baggie, it's tied off with a string. It's all full of water. There's water outside here and water inside the baggie too, except for one thing. This baggie isn't completely full of water. Somebody's put some sand down in the bottom of it. Well, there's a couple tablespoons of sand in that baggie. What's that baggie going to do if you put it in the lake? Going to go up? Going to go down? You know, if there's a little sand in there, that baggie's going down. Now I want to take another little baggie, same as the other baggie, all tied off, all full with water, except for a little air bubble at the top. What's this baggie going to do? It's going to go up. Everybody knows that. I'm not through. I'm coming to the important thing now. Here's another baggie, and this baggie is just full of water. There's no sand in it. There's no air in it. It's just pure water. It's completely filled with water. What it's going to do? What's it going to do? It's not going to go up like the air bubble baggie. It's not going to go down like the sand baggie. It's going to stay right there. A baggie full of water stays there. In fact, what this pool basically is, if we leave it alone, it's a pool of stagnant water. It means the water stands still. It doesn't go up. It doesn't go down. It just, all the water stays there. The baggie full of water will just stay there. There's a fancy word called neutral buoyancy. Of course, we know that's true, and we take it for granted. But it is nonetheless a marvelous thing. Because this baggie full of water is full of water. It has weight. Well, if it has weight, then why in the hell doesn't it fall down to the bottom? Because there's pressure on it from the surrounding water. And there's more pressure on the bottom of the baggie than on the top. And there's just exactly enough more pressure on the bottom than the top to balance the weight of the water inside. That's an amazing thing. And it stays that way if we change the shape of the baggie. So now the baggie has some other shape. We didn't take any of the water in or out. We left all the water that was in before in, but now it has a different shape. So now all the pressure forces are pointing in slightly different directions on the surface. There still is enough extra force on the bottom compared to the force on the top to exactly balance the weight of the water in that baggie. That's the pressure on the outside, gives exactly enough extra force on the bottom to balance the weight of the baggie. Let's put some numbers in this thing. 10 pounds of water in the baggie. Then there's a certain pressure pushing on the top of the baggie. Maybe it's 2 pounds pushing on the top from the water pressure above. What must be the water pressure pushing from the bottom of the baggie? Well, you know, if it's water, there just has to be 12 pounds of pressure pushing on the bottom of the baggie so that the net upward lift will be 10. Well, now I want to do a little trick. Somebody turns off the lights, and while nobody's looking in the dark, I sneak the 10 pounds of water outside of this bag. I take it out, leave the bag empty, but then I refill it. I don't change the shape of the bag. The bag has exactly the same shape that it had before. This time I put in it 18 pounds of sand. But supposing I'm down in the water and I want to hold this bag up, will I have to use 18 pounds of force to hold it up from going down? Yes or no? No, because the water itself is lifting with what force? The water itself, the surrounding water, is capable of putting a lift on that bag of 10 pounds. So how many pounds are left for me to hold up? 18 minus 10 is 8. I only have to support that bag with 8 pounds of force. And now you can begin to see how the water helps hold up the bag. Now I'm going to take out that 18 pounds of sand. And the bag is empty again, but I'm not changing its shape. Its volume and shape stay the same. And now just for the devil of it, I'm not going to put in the 10 pounds of water that was in there. I'm going to put in 8 pounds of chicken feathers in there. Well, now we got a problem, because remember what the rule was before, that you subtract off the 10 pounds that were originally in there for the water. Remember when we had the 18-pound thing, the rule was we took the 18, subtracted the 10, and got 8 left, and that was the weight. But now look at the situation. We have 8 pounds in there. 8 pounds minus 10, holy cow, you're going to have a negative number. You're taking away too much. What are you going to have? 8 minus 10 gives you minus 2. What does it mean? It has negative weight. Negative weight means just what you think it does. It's pushing up. It has, instead of having weight pushing down, negative weight pushes up and it wants to come up. And so that's the effect. So now, if I want to keep this bag the way it is, I don't have to hold it from the bottom. I have to hold it from the top. How many pounds of force do I have to put on the top? 2 pounds of force to keep it from rising up out of the liquid. Famous rule. Of course, what we're finding here is the famous rule of Archimedes, that if you want to find out how much an object weighs underwater, and they use a fancy word they call the buoyant force of the water. The buoyant force of the water on an object that's in the water is you figure out how much water would fill the thing and how much that water would weigh. How much would the water weigh that would fill the thing? And you subtract that weight of water from the weight of the thing. Now sometimes if you subtract that weight of the water from the weight of the thing, you still have a good deal of weight left. That means that the thing underwater still is heavy, it just weighs less. But sometimes when you subtract the weight of the water from the thing gets a negative weight. And that means it's going to be a force on it, a buoyant force that's going to lift it up to the surface. Let's see what happens when you finally get to the surface. Surface of the liquid, and here is a beach ball. And we will say that this ball weighs 8 pounds, but the water that would have filled the ball weighs 10 pounds. If we'd fill the ball with water, it would have weighed 10 pounds, but it's filled with rubber, so it only weighs 8 pounds, so there's a force that pushes it up. Well, how far does it push it up? Eventually, this 8-pound thing begins to get out of the surface. It begins to come through the surface. The rubber still weighs 8 pounds, but the buoyant force now is only the buoyant force not of 10 pounds, but only the buoyant force for the amount of water that would fill this part of it that still remains underwater. Remember, if we had the whole thing underwater, the water that would have filled the whole thing weighs 10 pounds. But now when it begins to peak up above the surface, the amount of water that we worry about is only the water that would fill the part that's still under here. And this thing peaks up until just the water that would fill here would weigh 8 pounds. And then the thing doesn't come up anymore. Well, I want to go back to the battleship finally to end the thing. When we began, we said that an object will float if it displaces its own weight in water. That was the rule that we used. And you say, how can it displace its own weight in water? The battleship weighs many, many tons. The little bit of water that's in that tub only weighs a few pounds. You see, this is a nice example of how dangerous it is to just play with words. When you just think about the words can say things that don't mean anything. This happens all the time. When they say a ship displaces its own weight in water, the water they're talking about is not this little bit of water that you see in the tub. It's the water that you don't see. It's the imaginary water that would fill the inside of the ship. Imagine that this ship were filled, the hull were completely filled with water. How high should the hull be filled? Right up to the red line on the hull. Now, of course, the hull isn't filled with water, because if the hull were filled with water, the ship would be ruined. The inside of the ship should and must be dry. There is no water in the inside. And yet the water they talk about when they say a ship displaces its own weight in water is that imaginary water that would fill the inside of the ship. So you have to really understand what the words mean. Later on, of course, in physics, people use equations because there are terms in the equation, and people use those equations but don't really understand where the numbers come from or what the meanings of the letters are. And then they get in terrible trouble too. So this is a simplistic example, but it shows the case. This war is over. Now that I've finished my little talk on why things float, let's suppose that we have some water, and here we'll go to our lake of water again. And down underneath the water, I have a little block of wood. And here's a little block of wood. And of course, you know, the wood won't stay there by itself. If you leave it alone, there's going to be a force pushing it up to the top, and you'll have to hold it down. That's called a force of buoyancy. The question I'm put to you is this. Suppose you take this little block of wood and you put it down deeper in the water. Let's put it down here. Of course, down here, there's also going to be a force of buoyancy on it. But down here, when it's deeper in the water, of course, there's more pressure on it. We all know that. Now, what's going to happen down here? Is there going to be more buoyancy? Is there more force pushing it up? Or maybe down here, there'll be less force pushing it up. Or maybe down here, there'll be no force at all pushing it up. Or maybe the force down here will be the same as it was up here. In other words, when you take it down below, just because you bring it deeper down in the water, the buoyancy doesn't increase or decrease. The force that's trying to make it pop up is the same. What do you think is the answer? I'm not going to give the answers right now. I'll give the answers at the beginning of the next lecture.